you all. Hopefully you can all see my screen.
Yeah, it's good.
Okay. So today I'm going to talk to you a little bit about thermal energy. And I consider thermal energy as a multifaceted area where we could treat it as a resource. I think primarily it's going to be a resource. In some cases, if you're not careful with it, it could become a waste. But I think the future, and one of the things that I'm most interested in, is how we can use this thermal energy to modify processes in either geotechnical or geoenvironmental engineering. So using the thermal energy as a tool. So hopefully today I'm going to go through many different examples of some topics. I'll try to go into some depth so that you understand some of the tools we need to use to solve these problems, but also just give you a broad overview of this area, because I think it's a pretty exciting field. So one of our, there are some other motivations, but I think the primary motivation, the reason that we're working on this topic is trying to address the high energy use of buildings. These are statistics for United States. These are going to be different in every country, but in the United States, heating and cooling of the buildings consume almost half of the energy required for the building, for the buildings themselves. And if you look at the building sector as a whole, it consumes about 40% of all of the energy in the country. But even then, it consumes a lot of the electricity and natural gas. Both of those, electricity generation and natural gas, contribute to large carbon emissions. And as we know, climate change is accelerating. So if we can do ways to make our buildings, do things to make our buildings more efficient, hopefully we can try to mitigate the effects of climate change. And an interesting thing, this is a nice breakout of the different types of energy that are used for different types of heating and cooling. Cooling is really dominated by electricity, so almost solely by electricity. Heating and cooking are mainly from natural gas in the United States. So these will vary from country to country, but I think generally worldwide, we try to share the common goal of making our buildings as efficient as possible. So I kind of decided to start out the presentation with asking a few general questions, even broader than geotechnical or geoenvironmental engineering, on how thermal energy can be used, or how it can affect these concerns about building energy use. So first, how can we obtain thermal energy? We know that the sun is giving off radiation and it's heating our planet every day, half of the day. So how can we collect that heat and make sure that we use it well? And if we're getting heat at the wrong times, how can we get rid of it and not have negative effects like these heat island effects? I'll talk about this later. And one thing, you know, that you're going to get a lot of heat in the summer and a lot of heat in the middle of the day. And that's not necessarily when you need it. So you're usually going to be needing it at night or in the winter. So how can we store that thermal energy? And we can always get heat from electricity or from burning fuels. So how can we use thermal energy in an efficient form? So that brings us to geotechnical engineering and geoenvironmental engineering. And I'm going to kind of focus this presentation on urban areas. Urban areas I define as pretty broad. It's just any place where there's a collection of people where you need to work together to provide resources. And I'm going to focus in this presentation on the shallow subsurface. There's many different ways that geotechnical engineers can get energy, including from very, very deep below the earth. But I'm focusing more on the zone of soil where geotechnical engineers are going to be doing their projects within the depth where foundations or excavations would be located. So how is the shallow subsurface a good, how can it help to answer these questions? First, the shallow subsurface is a good insulator and heat storage mechanism. We do get some fluctuations in temperature in the soil surface, But once you go below about 4 meters of depth, the temperature of the ground is relatively stable, and it approaches the mean annual air temperature at a given location. So that the subsurface is naturally going to store the solar thermal energy. Soils are very interesting. I'll show a couple examples later where heat transfer can occur due to both conduction, which is the most common, but as well convection as well. If you have flowing groundwater, if you have unsaturated soils, you're going to have vapor transfer. And geotechnical engineers in particular can help exploit these characteristics of the shallow subsurface because we're routinely installing structures in the subsurface. So if we modify them slightly, we can use them as tools to transfer thermal energy from one place to another. So as I mentioned, thermal energy can be a resource, waste, or a tool. In terms of resource, this heat that is naturally stored in the ground can be transferred to or from your building for space conditioning. We can access that naturally occurring heat instead of burning fossil fuels. So that's a very important sustainable resource. However, if you're not careful with it, and maybe you're just rejecting all of your heat into the ground, it could end up becoming a waste, especially if everybody in the neighborhood starts doing the same thing, because your heat transfer in the subsurface may affect the boundary conditions for your neighbors, and it'll still work, but your efficiency will start to go down. And then as geotechnical engineers, I think we like to make our systems more efficient. So I'm just going to try to show a few examples of how we can use thermal energy as a tool to perhaps improve soft clays with thermal consolidation, compacted soils with drying, landfill processes. This is a very important tool where we're storing our waste. How can we change the gas generation? How can we protect the liners? And finally, thermal remediation of contaminated ground, or even things like bridge deck de-icing if you live in a cold region. So I mentioned that as geotechnical engineers, we have many tools that we can use to try to address this energy issues in buildings. Some are deep, some are shallow. In this presentation today, I'm going to be focusing on these upper few categories that are focused on the shallow subsurface, where we're mainly focusing on exchanging heat with the ground or storing heat in the shallow subsurface. There's other fields like the deeper energy storage or storage of water behind reservoirs. And one thing we're going to talk about later is that we're not necessarily going to be focusing on generating electricity the same way that you would do it, get electricity from burning fossil fuels. That is possible in the geotechnical area by using binary cycle power plants or enhanced geothermal or these methane hydrates as a fuel. So we're not going to be focusing on that today. We're mainly going to be focusing on moving heat from one place to another when it's needed. So how are we going to do that? We're going to be using this tool of ground source heat pumps. There are some other options that we could use, thermal siphons, but ground source heat pumps are a tried and true approach. They've been used for decades now. The systems are getting more and more efficient and more reliable. So these are a tool to exchange heat from one place to another using closed loop systems where you circulate fluids. So in our case, we're going to be circulating fluid through a hole in the ground, either a borehole or a structural unit. And we're going to connect that loop of flowing fluid in the ground to a refrigerant loop. And it's the same refrigerant loop that we have in our air conditioning system or in our refrigerator. And that is going to exchange heat to move it from one place to another. So we're not going to be generating electricity. We're actually going to be consuming electricity, but it's an efficient way. We get maybe 4 to 1 of efficiency in moving heat from one place to the other. So the heat transfer in the soil surrounding this exchanger could be due to conduction and convection. And these ground source heat pumps can function in any location and with good efficiency if designed and used properly. You know that your air conditioning system, even when it's 50 Celsius outside, it's still able to reject heat into the hot outside. It's just not as efficient. So we can still use it in any location. These are just some more details of the way that we exchange heat. We have our water that's flowing through the ground loop here in this blue section. And that is going to be exchanging heat with the refrigerant, which is expanding and contracting as it moves through its own loop. So you mainly need electricity to compress the refrigerant to turn it back into a liquid, and then it will expand as you go through a certain nozzle, and then it's going to shed or absorb heat in either of those two phases. You can operate these heat pumps for cooling or for heating. Our ground temperature, as we mentioned, is going to be close to the mean annual air temperature. It's actually even higher than 10 to 15 degrees Celsius here in San Diego. But when we're trying to heat our building, we're going to be putting cold water into the ground, and it's going to heat up. So we're going to be putting almost close to freezing fluid into the ground. It's going to come back warmer. And then when we're trying to cool the building, we're going to be putting hot fluid into the ground. It's going to be shedding the heat into the ground and coming back a little bit colder. There's many forms on how we can arrange these geothermal systems in the ground. But the main ones we're going to focus on in this presentation today are borehole heat exchangers, where we make a hole in the ground and put a closed loop pipe into there, or to use our structural units, our energy piles in the ground. So today in this presentation, I'm going to focus on 6 topics. Some of them are going to be shorter than others, mainly on showing how this thermal energy could be a resource or waste, pure resource, or a resource and a tool. I was kind of trying to divide it into resource, waste, and tool, but in most cases, heat is always going to be a resource. So even when we're using heat as a tool, you've installed a system in the ground that you can use to exchange heat. So it's going to improve the ground, but you're also going to be getting the heat exchange capabilities. So thermal energy is always going to be a resource. So I'm going to talk about energy piles and a real building application. I'm going to talk about how we can store thermal energy from the sun in the ground, how we can extract heat from landfills, from municipal solid waste, biodegradation, how we can use excess heat to as a way to remediate contaminated grounds, how we can improve the capacity of piles in unsaturated soils, and how we can improve the capacity of piles in soft clays. So let's start going through each of these. Most of these applications are going to be involving energy piles, mainly because that's what we use as geotechnical engineers. And in urban areas, we usually don't have a lot of space where we can install heat exchangers, but we do have space to put the foundations beneath our buildings, as long as we're building a new building. There's many other options. Instead of putting the heat exchange pipes that you can see here in these different pictures inside of a reinforcement cage of a foundation to form the energy pile, we can also put those pipes inside of a retaining wall, inside of a tunnel, inside of a sewer, inside of the road. There's many ways to convert the earthwork we're doing into an energy focused system. Just as a couple notes on thermal design, we always want to make sure that the length of these pipes that we're putting into the ground as a heat exchanger is enough to absorb the heat pulses, either extraction or injection via conduction, without affecting the ground temperature. If we're doing heat storage, we do want to affect the ground temperature, as we're going to see. But if we're doing heat exchange, we want to avoid thermal overlap with the other heat exchangers. And we always want to do some thermal analysis, but if we want to do some quick rule of thumb calculations on how long of heat exchangers we need to absorb a certain heat pulse, there are some tools we could use. One thing to note is that when we're using energy piles or these other structural units, you always want to make the length determined by the structural requirements rather than the heat exchange requirements, because the energy pile the pile itself is expensive, and then the added cost to change them into an energy pile is relatively low. So we do know that heat exchange capabilities of energy piles are much better than those of these smaller geothermal systems. So one case history, I'll show just how energy piles work, and not only how they work, but how they could potentially be an issue that you need to be careful about. So this building was in Denver. I was professor at University of Colorado Boulder before I moved to San Diego. So you can see some snow on the ground here, which I haven't seen in a while. So they were building this building, and they were going to be putting a geothermal system into the parking lot. We spoke with the contractor and said, well, you have the geothermal system already. Can we convert a couple of the piles for this building into energy piles? And they said, yes. So we quickly had to come on site and mobilize and get everything working. So the system already has a geothermal system to provide the heating and cooling. The energy piles here were not meant to augment that. They're more for just an experiment. This is the plan view of all of the building piles beneath the building. You can see that there are a lot of these piles throughout the entire building. There's 60 of them. They're around 15 meters deep. We converted 2 of these into energy piles. The other geothermal system is out here in the parking lot. We had to be careful to choose piles that were close to the mechanical room. This pile B is at the edge of the building, and pile A is in the center of the slab. And all of these piles were different diameters, but these 2 that we were looking at were the larger ones. Some interesting aspects in Denver, there's a lot of urban fill. So the top few meters were this fill and sandy gravel, but below that, there's the famous Denver blue shale. So this is a expansive soil. We just had to deal with whatever we were going to deal with because we heard about the project and we were installing energy piles 2 weeks later. And we went there and added these heat exchange pipes to the inside of the reinforcement cage. We put some vibrating wire strain gauges to measure temperature and strain at different depths. And then we hooked everything up. We had to wait a few months for everything to get connected and the building to be constructed. But then the building went into operation, and we started to record for about 5 years the heat exchange capabilities. So some interesting, whenever you're in the winter, we had this is the cooling stage and the heating stage, and then in the spring and fall, there's always some days you're heating, some days you're cooling. So this gray line is basically the temperature difference between the inlet and outlet fluids. So you're shifting between heat rejection and heat extraction multiple times throughout the year. So those heat transfer processes that are happening, which are relatively stable, I think that just this process here is showing that the heat transfer is working. But those changes in temperature of the heat exchange process lead to changes in temperature of the foundation. Each of these little gaps that we can see here are due to some accidents when the data logger stopped working. So they're kind of like your blips on your heart meter. But you can still kind of fill in with your eyes what was happening during those periods. So I think thermally, we showed that these energy piles were working and it's very efficient. But one thing you have to worry about are these thermomechanical soil structure interaction. So one thing that happens when you heat the energy pile, it wants to expand. When you cool it, it wants to contract. So these are adding, and then the expansion is resisted by the frictional forces on the soil. So you're having compressive stresses during heating and tensile forces during cooling stresses. So looking at the strains that we measured, instead of having a very regular strain profile, we started to see some strains that there are some gaps in the data that you could see here, but you could see that there's a trajectory. It's not as stable. In the tops of the energy pile, it is pretty sinusoidal, but in the bottom, it started to deviate upwards. So this is where we kind of thought that there was a thermally induced drag down in that Denver Blue Shale layer. And when we started to process the data, we did see that superimposing these drag down effects on the bottom of the pile, we did see an additional compressive stress that was attributed due to this gradual thermal contraction of that claystone layer. So we could talk more about that later, but I just want to show that temperature had the positive effect that we were having the heat exchange, but it could potentially have a negative effect on the mechanical response. When you do look at the changes in stress and the changes in deformation, they're very small. So you do superimpose some additional stresses that you can see here due to this thermal drag down, almost 5 MPa, which is important. You need to take that into account. But overall, those negative effects are not big enough that they're going to affect the design of your system. So in that case, the temperature could be a negative aspect on your pile, but the benefits that you get from the heat exchange outweigh it in that case. So I just wanted to add some comments about how thermal energy could be a waste. So what happens if everybody in the city decided to adopt energy piles or geothermal heat exchange? So Kenichi Soga and his research group have done some very nice studies. They looked at the city of Westminster. They characterized all of the different types of buildings that were in this region, residential areas, commercial areas. And then they mapped what would happen if everybody used these geothermal systems. And anywhere that you see red means that there's a concentration. So that means that people are going to be affecting their neighbors. So that's something that we may need to worry about a long time in the future when people start adopting this more, that you could potentially be affecting your neighbors. But even if we don't have energy piles, we are, as our processes and our daily life is affecting the temperature of the ground naturally. So if we don't have heat exchangers, but we have a hot basement, that's going to be heating the ground. So this is another study by Kenichi Soga's group. And then also whenever you have tunnels going through the ground, that could lead to additional heating. So these are a couple cross sections through London, showing that anytime that you cross through a basement or through a train line, there's a big spike in temperature. And if you're in a sensitive material like London clay, it is possible that those changes in temperature could lead to settlements. And as our temperature at the ground surface starts to get warmer, if we're having climate change, we're going to shift that heat island effect downward into the subsurface, which could have these negative geotechnical effects. So that's a place where the thermal energy could be a waste. And very close to home for Krishna is a recent study from Alessandro Rottaloria from Northwestern University. He mapped out the temperature distributions throughout many locations in Chicago downtown, saw that there was a gradual rise in temperature in many locations. And then he used some simulations to show what would happen if you had soft soil, stiff soil, or hard clays, if you're having expansion or potential contraction. So if you're increasing the temperature, you could start to see settlements. So this was a big, it received a lot of publicity. But one tool is that we have these geothermal heat exchangers. That may be a way, if we're starting to heat up the ground, we start to extract that heat and redistribute it to other locations where the heat is actually needed and it's not going to cause problems. Okay, so shifting gears, I think the energy piles are important to talk about a lot, but let's talk about how we can use that heat for other purposes. So instead of exchanging heat, what happens if we say we want to put a lot of heat in the ground and store it there? And we could get that heat from industrial processes or from burning fuel, but we also have naturally occurring heat at the ground surface from solar thermal energy. And that is gradually going into the ground, but what happens if we want to take it and force it into the ground in a concentrated location? So many locations in the US have a very high solar fraction, but even in the places that don't have a high solar fraction, they do receive enough energy to provide heating in the coldest parts of the year. but that heat is coming at a time where it's not needed. There's two examples of locations that I think would be characterized as not ideal in solar areas, where solar thermal energy is collected and stored in the ground and used to provide all the heating. One is in Alberta, Canada, another in Denmark. Denmark is one of the pioneers for having these solar thermal plants where they collect the heat and store it in the ground and then use it to provide district heating. So one of my things that I've been advocating is to try to build these in the United States. We built a test system here in San Diego. This is the one from Canada here. You can see it has a collection of almost 100 boreholes that have a very close spacing. So different from regular geothermal heat exchangers where you don't want to affect each other. You want to have these boreholes very close to each other so you concentrate heat in a certain location. And it would be nice if you were able to insulate in the ground and insulate on the surface so you can keep the heat there, but it's very costly to put a vertical heat storage system around this, your borehole heat exchangers. And the way that these work is you inject heat from the solar systems in the summer, you store it in the fall, and you extract it in the winter, and then you repeat on and on. So you're heating the ground in the summer, you're going to have some heat loss because it's not perfectly insulated, and then you're going to extract it, so the temperature is going to go back down, and then when you eject, it's going to go back up. So let's see some real data on how these work. So the first thing before we started to build our own system in San Diego is we wanted to simulate the system that was there in Canada. So we did some simulations in Tough. So these are the heat injection. So it's different from those temperatures that I showed for heating and cooling of the ground. We're injecting very high temperatures, like 60 to 80 degrees Celsius. And then when we're extracting, we have colder temperatures, somewhere around 30, that we're trying to pull that heat back out in the winter. So these are just some plots showing that as you go from season to season, you actually start to store more and more heat because you never extract all of the heat that you've injected during the summer. So if you look at things in terms of efficiency, the efficiency is low, but the efficiency here is defined as the heat extracted divided by the heat that was injected. So the efficiency is low, and in 1 year it goes down, and we were puzzled why that happened. And it was because you injected a lot more heat that year, but you didn't need to extract as much in the winter. So it wasn't as cold of a winter, but it made it look like the efficiency was low, even though you were able to get all the energy that you needed, which maybe indicates that this way to define efficiency is not the best. So even though this system was able to store enough heat in the summer to provide heating for 55 houses in the winter in a very cold location, there are some problems there. This location in Canada was in saturated soil, and there was a natural groundwater flow at that location. And one check that we did was we changed the hydraulic conductivity of the ground. And as your hydraulic conductivity started to get higher and higher, you started to end up having some convection cycles forming. And those convection cycles take heat away from your heat storage system. And those changes in permeability in this case are not so high. Just by 1 order of magnitude, you start to see some convection. So one idea we had was, why are we putting these in saturated soils? We could put these in unsaturated soils that are close to the ground surface, and we could take into account, we can use the fact that unsaturated soils have a lower thermal conductivity. So instead of having the heat losses due to groundwater flow, we can suddenly use the shallow subsurface as a natural insulator. But the one problem is that it's a lot more complicated to study the heat transfer. So we did some simulations. I'll show you some equations later. But we looked into the case where we were studying the convection and conduction. And if you take into account convection, you can actually inject heat faster And then because it's unsaturated, you have a lower, more storage of heat, mainly because when you inject heat, you're having a drying effect. So you've reduced the thermal conductivity, so you have a greater retention of heat near your heat exchanger. So when you have convection and conduction, you have a faster heat gain because of these coupled heat transfer processes, and you have a slower heat loss due to the drying effect. So we decided to build one of these heat storage systems here in San Diego. Unfortunately, it's very unsaturated in this region. So we had a large unsaturated layer. We installed 13 boreholes to a depth of about 15 meters, installed a lot of instrumentation into the ground to measure temperature changes. These are some pictures of us drilling. We put these 13 boreholes, 4-inch diameter boreholes, pushed in a heat exchange pipe, backfilled it with sand bentonite. It was hard. In the future, I want to study using energy piles under the building instead of having these boreholes, because energy piles have a little bit more control over holding the holes open. But once we installed everything, we connected the pipes together and sent those to a manifold, put an insulation layer and a vapor barrier on the surface. We collected heat from these solar thermal panels, stored the heat in a tank, and then used a manifold to inject the heat over time. These are just the heat transfer that we got over a certain day. So we had a very high heat transfer rate during the days, and then injected that into the ground. And the air temperature is fluctuating, but we got very high heat transfer rates into the ground. And then over the course of a summer, we injected the heat into the ground, and we had 2 different heat storage systems. So here's just some pictures of how we heated up the ground. And we reached temperatures of about 35 Celsius. In the industrial systems, they're getting up to about 60 Celsius. But over the course of a summer, I think that was pretty good. And then we let it rest, and we just tracked the heat loss over time. So we had the heat spreading due to the ambient cooling. And we saw that the temperature of the ground increased within this array. So there's a lot of room to keep improving upon this in the future. I want to keep building upon that and maybe even expand into using energy piles. But for the purposes of moving on, let's talk about some other cases where we can use heat as a tool. So one of these is in municipal solid waste. It's well known that methanotropic activity has heat as a byproduct. So we can just extract that heat and use it for heating buildings. We could also use it to augment industrial applications on the landfill site. But I think that there's some more opportunities that we can look at in the future. If we're going to be installing these heat exchange systems there, we can extract that heat and control the temperature on the liner systems. One good thing is that if you control the temperature, you could prevent desiccation of your clay liner beneath the waste. You could also potentially have heat exchangers inside of the waste and keep the temperature of the waste ideal so that you could have as much methane generation as possible if you're trying to get electricity generation. And then we know that if the temperature is too high or too low, the biological activity is not ideal. So if you want to maximize the settlement rate, you can control the temperature using heat exchangers as well. So we had a landfill. This is the San Diego area. This is where I'm located now. We worked with Republic Waste Services at the Sycamore landfill. So they were building a new landfill cell, and they were starting from this side and said, you can have a small area and put a test facility in here. And over time, we're going to build stuff on top of this. So this has to be a temporary project. So they put in waste in different layers. And as they put the waste, we put different heat exchange systems. And we put these into a serpentine configuration where we could circulate fluid through there. This is just a picture of how the heat exchangers were laid out. This is the waste being placed as it's coming towards us. And it would cover this and come up to the expected edge. And then we would put another layer of heat exchangers and they would go backwards, like spreading peanut butter. And we put some different temperature sensors there. One thing you have to watch out for in San Diego are these palm trees. They cut them into small sections and they roll down this hill. And they beep their horn if they've set off a palm tree roll down the hill. So we covered these with a small layer of cover soil just to protect the pipe, filled the pipes with water so that they would be protected. And then this was the final slope of the waste. We had to dig out all of the pipes and everything at the end and connect it to a chiller and a generator because we didn't have power out there. So we had a generator, and over the course of about a couple weeks, we extracted heat from the waste and measured temperatures. But first, before we did that, we allowed everything to heat up. This was back in 2017. So we reached about 51 Celsius in the waste. And then we did a heat extraction test for 2 weeks. Had to go and measure temperatures. So there was some effect of the air temperature on the system, but overall you can see the heat extraction happening. And then we can look at the thermal conductivity of the waste, and the different layers had some different thermal conductivities depending on their mixture. But this information is useful if you want to design a system for heat extraction. So we were able to extract the heat from the waste and affect the temperature of the waste as well. So if you're trying to control the temperature, it's possible using these geothermal heat exchangers. Moving on, because we're kind of running out of time, thermal remediation. So if you have extra heat, it may be possible to have these heat storage systems installed in a contaminated ground and reach 40 to 60 Celsius. That's not enough to really burn off the material and completely vaporize it, but it is good enough to cause coupled heat transfer and water flow. So really only high temperature applications have been studied for thermally enhanced soil and vapor extraction. But taking these geothermal systems and putting them into the ground could be a way to make this work better, because your geothermal systems, you have sustained heat sources that you can leave there for a very long duration. So we haven't really had the opportunity to do a lot of test projects with this, but we've done some laboratory scale tests. We did a column test where we heated the column from the outside and allowed vapor flow to go upwards. And we collected samples of the gas over time, and also the effluent to see how much we were extracting. We extracted a lot of water, which was good. But unfortunately, we used diesel as the contaminant, and diesel is not the best. It's not very volatile. We should have used a different contaminant. But we did extract some diesel, but it wasn't as interesting as we'd like. But this is just another idea for how we could use heat as a tool. Last two topics are how we can use heat to improve energy piles in different problematic soil layers. Both of these applications, we use centrifuge testing, mainly because to do these in the field could be very complicated. And if we have a frame inside of the centrifuge, we can actually heat the soil up and then do pull-out tests or compression tests to see the effect of temperature on the capacity, to see the positive effect of thermal improvement. So just a note about centrifuge modeling. We can use the centrifuge to replicate the stress state in a small scale model. So we do the model spinning in the centrifuge, and then its behavior is the same as a prototype. Heat transfer doesn't necessarily scale, but when we reach thermal equilibrium, we can say that we're at a stable case. So we need to make small scale piles in this case, put them into a tank of soil. We did sand and silt. And the nice thing here is that we can apply loads and measure the bearing capacity. So we did some tests where we heated piles up to different temperatures, waited for everything to stabilize, and load them to failure. Sand is kind of boring. When you heat it to different temperatures, nothing changes. Silt, though, when you heat it, we saw very different capacities. So we saw this as, we didn't know why exactly this was happening. We thought it was maybe due to radial expansion, but we found later it was due to this thermally induced water flow. So we said, heat is a way that we could dry the soil and increase the capacity of our pile as we heat it. So we had some sensors we could measure as the temperature goes up, the water content goes down. We have a drying effect. We had to do some modeling. I'm not going to go into the details, but if you have questions, we can talk about it later. We have to do a lot of calibration for the model to get it to work. But we're able to match the changes in temperature and changes in water content from the tests, and mainly show what is happening right at the pile interface. And we could see that there's a very large increase in effective stress at the interface. And the shear strength, or the interface shear strength, is dependent on the effective stress. And we used some different pile models to predict the increase in capacity of the pile as an increase in temperature due to this drying effect in the unsaturated soil. So that's an interesting thing that we can do. Also, what happens if we have a completely saturated soft layer? We know that in soft soils, there's potentially a lot of volume change. So one technique we can do is we can use heating to apply a large temperature change. An interesting thing that happens in saturated soil is that the water will expand more than the solids. So you get an increase in pore pressure due to the temperature, but that increase in pore pressure is going to dissipate over time. And as that pore pressure dissipates, you're going to have a change in volume and an increase in shear strength. So we did some experiments where we heated a soil and allowed it to cool, and measured the shear strength at room temperature, after heating and after cooling. And a heat and cooling cycle leads to greater strengths. So this is a room temperature test after heating and after heating cooling cycle. So by going through this process of heating the soil and cooling it off, you've increased the shear strength. So that's a thermal soil improvement. This has been done before in full scale in Thailand, where they've put in heat exchangers into the ground and watched how the heating process leads to increased settlement over time. But we wanted to look at the effect on piles. So we had a tank of soil. This is the centrifuge that we have in San Diego. And this is a soft clay layer surrounding a pile. We heated everything up, and then we did a pull-out test. So there's a lot of other data that I could show, but interesting thing is that the temperature didn't affect the stiffness, but it affected the peak shear strength. So for these three tests, we saw almost 100% increase in pull-out capacity after we've heated it by 60 degrees. So that's about the temperature that we would expect during a heat storage application of energy piles. Okay, so I kind of touched on many topics there, but hopefully I gave some examples of how thermal energy could be used as a resource. Mainly, we can access that heat with ground source heat pumps and energy piles. Heat could potentially be a waste. It could accumulate heat in a given location. We need to make sure that we're working with our neighbors to look at district scale analyses. But we could also use this heat as a tool. There's many opportunities for using heat for positive purposes. I showed you some things about landfills, potentially how we could use it to remediate ground, how we could dry soils, and how we could cause thermal consolidation. So I want to leave a few minutes for questions, but a lot of students over the past 15 years or so have helped a lot, and I'm very grateful